Hey everybody, and welcome to our third numerical analysis lecture. We're still studying root finding algorithms or solutions to equations of the form f of x equals 0. And today we're talking about the bisection algorithm. Here's what we need, and here's what it does. The application: solve equations of the form f of x equals 0, where f of x is continuous and has at least one real root. Now, something we should notice here: the restrictions here are not quite as rigid as what we had for Newton's method. Newton's method requires that f of x be differentiable. With the bisection algorithm, f of x doesn't have to be differentiable. It just has to be continuous. In other words, the graph of f of x just has to be one long connected piece of spaghetti. And of course, let's see, one other restriction on this function, obviously, is the fact that this equation does have to have a solution. So f of x does have to have at least one real root. As input, we define the function f of x, most likely as a function subprogram. And as input, we prompt the user to enter two x values, x equal a and x equal b, such that their product is less than 0. Now, why would we want such a thing? Well, we'll get into that in a minute. But we do have to prompt the user for two x values, x equal a and x equal b, such that their product is less than 0. If they try and they fail, the program will prompt them continuously until either they do provide such x values or they choose to abort the program. And finally, as input, we have the tolerance, the maximum allowable error. Okay, this is what the algorithm does. It solves equations of the form f of x equals 0, where f of x is continuous and does have at least one real root. This is what we have to input into the program. Now let's find out why it works. Here is in part a reason why the bisection algorithm works. If f of x is continuous on the interval ab, and if the product of f of a and f of b is less than 0, then the intermediate value theorem guarantees that there exists an x value, x equal x naught, where x naught is between a and b. The intermediate value theorem guarantees that there is such a value, x naught, between a and b, such that f of x naught equals 0. The intermediate value theorem guarantees that such an x value exists. The fact of the matter is, it may be the case that more than one of these x values exists, but there's at least one x value between a and b such that f of x naught equals 0. Now, before we look at the intermediate value theorem, maybe I better clear up the mystery behind this requirement that the product of f of a and f of b is less than 0. So here's the story about f of a times f of b being negative. significance of the requirement that f of a times f of b is less than 0 is that f of a times f of b is less than 0 if and only if f of a and f of b are of opposite sign. So if f of a and f of b are of opposite sign, then f of a times f of b is less than 0. And if f of a times f of b is less than 0, then f of a and f of b are of opposite sign. So this restriction is put in place just so that we can be absolutely sure that f of a times, absolutely sure that x equal a and x equal b are such that f of a and f of b are of opposite sign. And think about it, it makes sense. If f of a and f of b are both positive, we have positive times positive is positive. If f of a and f of b are both negative, we have negative times negative is positive. The only time when the product of two numbers is negative is when they're of opposite sign. So this condition guarantees that f of a and f of b are of opposite sign. One's positive, one's negative. Now, why? And it doesn't matter which one's positive and which one's negative? Absolutely not. We don't care which one's positive, which one's negative, just as long as they're both of opposite sign. And why is that important? To understand that, we have to know what the intermediate value theorem tells us. So let's take a look at the intermediate value theorem. And then we're going to look at a special case of the intermediate value theorem that applies directly to the bisection algorithm. The intermediate value theorem. Suppose that f of x is continuous on the interval AB. So that's our first condition. F of x is continuous. And suppose that for some real number, y equals c, either f of a is less than c, which in turn is less than b, or f of a is greater than c, which in turn is greater than f of b. So two conditions here. F of x is continuous on this interval, and either f of a is less than c, which is less than f of b, or f of a is greater than c, which is greater than f of b. If these two conditions in our hypothesis are satisfied, then the intermediate value theorem guarantees us that there's some x value, x naught, between a and c, such that f of x naught equals c. So if f of x is continuous, and either f of a is less than c, which is less than f of b, or f of a is greater than c, which is greater than f of b, then we're guaranteed that there's an x value, x naught, in this interval between a and c, such that f of x naught equals c. Now, why is this the case? We're going to look at both situations, the situation where this is the case and the situation where this is the case. And we're going to do this in picture fashion, and it's going to be so obvious it'll tickle you to death, I guarantee it. Okay, here's the scenario. Whoops. Okay, here's the scenario. f of a is less than c, which in turn is less than f of b. Here's the point on the graph of f of x, a f of a. Here's the point on the graph of f of x, b f of b. And we can see that f of a is less than c. F of a lies below c on the y-axis. And c in turn is less than f of b. C lies below f of b on the y-axis. Here's the point on the graph of f of x, a f of a. Here's the point on the graph of f of x, b f of b. And what am I missing here besides the graph of f of x? The fact that f of x is continuous. Remember what the graph of a continuous function looks like. It's one long connected piece of spaghetti. There are no breaks, no interruptions. So from this point, a f of a, to this point, b f of b, that graph is one connected piece. So let's see. The graph may go like this, and the graph may go like this. But you know, if the graph is one connected piece, this section of the graph and this section of the graph have to be connected. And we can't get from here, below the line y equals c, to here, above the line y equals c, without going through this line, y equals c. We can't get from here to here without crossing that line. So here's what the graph could look like. And guess what? Right here, right at this point, the graph crosses the line y equals c. So we know what the y coordinate of this point is. The y coordinate of this point is c. And what's the x value? We'll call it x of naught. Because this point has x coordinate x of naught, and because this point is on the line y equals c, the y coordinate of this point is c. But hold the phone. This point is also on the graph y equals f of x. And I should have that somewhere. Where could I put this where it won't crowd out everything? Okay, good. This is the graph of y equals f of x. So guess what? This point right here, which is on the graph of y equals f of x, has x of naught as its x coordinate. But since this point is also on the graph of y equals f of x, yep, you guessed it, it's going to have a y coordinate of f of x naught. And these 2 points are one and the same point. Right here, where the graph of f of x crosses the line y equals c, we have the f of x value equal to c. So in the case where f of a is less than c, which in turn is less than f of b, there's some x value, x equal x naught, between x equal a and x equal b, such that f of x naught equals c. This is exactly where it happens. Now, just for the case of being thorough, we're going to look at case 2 also. We're back. And this time, f of a is greater than c, and c in turn is greater than f of b. So here's f of a greater than y equals c, greater than f of b. And since f of a is greater than c, the point a f of a lies above the line y equals c in the xy plane. Because f of b is less than c, the point b f of b lies below the line y equals c in the xy plane. And let me sneak this in. There we go. And again, f of x is continuous, which means that this point a f of a and this point b f of b are joined together by a graph that's one connected piece, one long connected piece of spaghetti. No breaks, no interruptions, no holes. And somehow, with one connected piece of graph, we've got to get from here to here. And if the graph is connected and it's one piece, we can't get from here to here without crossing the line y equals c. Somewhere around here, the graph has to cross the line, or has to cross the line y equals c. And where it does, aha, there's our point. We'll call the x-coordinate here x of naught. And this is the point x of naught, c. Why? Well, we gave the x-coordinate of this point the name x of naught. And this point is on the horizontal line y equals c. So the y-coordinate of every point on this line is c, including the y-coordinate of this point. So this point is x of naught c because it's on the line y equals c. But this point is also on the graph of y equals f of x. And so the x-coordinate of this point, x of naught, the y-coordinate of this point is going to be f evaluated at x of naught, because this point is on the graph of y equals f of x. These are one and the same point. So again, right here, we have f of x of naught equals c. That's how the intermediate value theorem works. And are we done? Nope, not quite. We want to look at a special case of the intermediate value theorem that is tailor-made for the bisection algorithm, which is what we're working on. So let's look at that special case. Everybody, before we get to this special case, I looked at something on the board that I need to correct. F of x is continuous on the interval AB, and for some real number y equals c, either f of a is less than c, which is less than f of b, or f of a is greater than c, which is greater than f of b. Then there exists an x naught in the interval, and this is what I have to correct. I had c written here. Please correct it. There exists an x naught in the interval a, b, such that f of x naught equals c. So in the previous part of our lecture where I said there exists an x naught in the interval AC such that f of x naught equals c, please change the c here to a b. This should have been b. Okay. Here's the special case of the intermediate value theorem. Suppose, 1, that f of x is continuous on the interval AB, and 2, suppose that either f of a is less than 0, and 0 in turn is less than f of b, or suppose that f of a is greater than 0, and 0 in turn is greater than f of b. In other words, f of a is negative and f of b is positive, or f of a is positive and f of b is negative. F of a and f of b are of opposite sign. Then in this case, there exists an x value, x of naught, in the interval AB, such that f of x naught equals 0. And again, we'll draw out these two scenarios to make it perfectly obvious why that has to be the case. Here's the first scenario. F of a is negative, f of b is positive. So f of a lies below the y-axis, f of b lies above the y-axis. No, I'm sorry. F of a lies below the x-axis, forgive me. F of b lies above the x-axis, also known as y equals 0. And f of x is continuous, which means that the graph is one connected piece going from here to here. And if the graph is one connected piece, we can't go from here below the x-axis to here above the x-axis, you guessed it, without crossing the x-axis somewhere in between. And right where we cross the x-axis, we call this x of naught. And since this point is on the x-axis, the y-coordinate is 0. So this is the point x of naught 0. Well, there's something else we have to consider. This point is also on the graph of y equals f of x. So since this point is also on the graph of y equals f of x, the coordinate is x of naught, the x coordinate. The y coordinate is f of x of naught. These 2 points are one and the same point, right here. So what does that mean? Right here at this point, f of x naught and 0 are one and the same. Right at that point. Now we'll look at case 2. Why not? Just for the sake of being thorough. Here's the graph of y equals f of x, and this time f of a is positive. So the point A, f of a, lies above the x-axis. And this time f of b is negative. So the point B, f of b, lies below the x-axis, also known as the line y equals 0. And again, f of x is continuous. So the graph of f of x is one connected piece of spaghetti. And this graph that's one connected piece has to go from here, the point A, f of a, to here, the point B, f of b. And it's one piece. Well, how does a graph that's one piece, one connected piece, go from here to here? Somewhere in between, it has to cross the x-axis, doesn't it? And right where it does, we'll call this point x of naught. And since this point is on the x-axis, the y-coordinate has to be 0. But since this point is also on the graph of y equals f of x, the x-coordinate is x naught, and since this point is on the graph of y equals f of x, the y-coordinate has to be f of x. And again, these 2 points are one and the same point. They're both this point right here. So that tells us that f of x, excuse me, let's see, if the x-coordinate is x of naught, the y-coordinate is f of x of naught. Please forgive me. These 2 points are one and the same. So the y-coordinates have to be one and the same. F of x of naught is the same as 0. So right here at this point, f of x of naught is equal to 0. Now that's the special case of the intermediate value theorem that we wanted to look at. And it's this special case of the intermediate value theorem that we're going to use in our bisection algorithm. Okay, back to the bisection algorithm. Given that we do have a continuous function f of x, and x values xa and xb such that f of a and f of b are of opposite sign, we compute the midpoint, c equals a plus b over 2, of the interval ab. This makes sense. C is the midpoint. If we add a and b together and divide by 2, what do we get? The average of a and b. That's the midpoint of the interval ab. Now, given this midpoint and the fact that f of a and f of b are of opposite sign, exactly one of the following 3 statements must be true. There are 3 possible cases. One of them has to be true. Let's look at it. Before we do, I'm going to make one assumption, just for the sake of simplicity. Without loss of generality, we're just going to consider the case where f of a is positive and f of b is negative. The same kind of logic holds if f of a is negative and f of b is positive. So we're not going to consider both cases. This one case will be typical and representative of both cases. Now let's look at those three statements, one of which must be true. The first thing that could happen is that f of c might actually be equal to 0. Well, aren't we looking for the value of x that makes f of x equal 0? So if f of c equals 0, this is the value that we've been seeking. Our x of naught is equal to c. Here's x equals c. This is where the graph crosses the x-axis, right at the midpoint of our interval. And since this is on the x-axis, the y-coordinate is 0. This point is c, 0. But since this point is also on the graph of y equals f of x, this point is also cf of c. They're one and the same point. This is where f of c equals 0. If that happens, we have what we're looking for. And we print solution is x equals c, and we terminate the program. We're done. This can happen. It probably won't. It's unlikely that this will happen, but it could happen. Just like it's unlikely that our house will get struck by lightning, but it could. So we have a lightning rod on our house, and we have our electrical circuit box grounded and all of that sort of thing. Probably won't happen, but it could, so we prepare for that eventuality. F of c equals 0. Probably won't happen, but it could. So in our program, we prepare for that possibility. Now let's look at the other two cases. Here's the second thing that could happen. F of a times f of c is less than 0, which means that f of a and f of c are of opposite sign. So here's f of a above the x-axis. Here's f of c below the x-axis. And that means that the graph has to cross the x-axis somewhere between f of a and cf of c. And right here where the graph crosses the x-axis, here's the value of x that we're looking for. And right here at this point, this is where we have our solution, f of x naught equals 0. Now let's write out in words what that really means. Okay, before I continue, in the picture that you have drawn, please mark this point B. I hadn't marked it as anything, but this is the point B on the x-axis. Before, I just didn't have anything. Please mark this point B. Well, here's what we have. We have the situation where we know that our solution is between A and between C. So do we really need the interval from C to B anymore? The solution that we're looking for is not here. So, since we know that the solution is in the left interval from A to C, why not just take this interval from C to B and throw it away? We discard the interval C to B by making the following assignment. This is clever as all get out. It's so simple but so effective. We want to get rid of this interval. So what do? We just set B equal to C. So guess what? This is now our new B. And we're working with this interval from A to B. This interval from A to B with the new value of B now contains our solution. That's so clever, so devious, so sneaky, I just love it. Now, there is a third possibility that we have to consider, so let's look at that. Okay. Whoops. Third possibility. Here's the third possibility. F of A times F of C is positive. And that means that F of A and F of C are of like sign. So if F of A is above the x-axis, as we're assuming, F of C has to be above the x-axis also. And that means the graph has to cross the x-axis somewhere between C and B. So right here is our point x of naught 0. This is where f of x naught equals 0 is, somewhere between the points C and B. So let's see what that means for us. Our solution, x of naught, is in the interval from C to B. So what do we need this interval, A to C? What do we need this interval for? We don't need it, do we? We do not need this interval. So why not just throw it away? We discard the interval, we discard the interval AC. This interval right here, we throw it away, we don't need it because the solution is in the interval from C to B. So we discard the interval AC by making the following clever assignment. We just let A equal C. So we take the value C, our midpoint, and we assign that value to A. So this is no longer A. This is our value A. And we have our solution confined to an interval that's only half as long as the original interval. Well, that's progress, but it doesn't seem like much progress. But in fact, it is. After forming our new interval, AB, compute the midpoint C, which is just the average of the two endpoints. And we follow the same three-case procedure with this new interval, testing to see which of these three cases is going to be true. Either f of c equals 0, f of a times f of c is less than 0, or f of a times f of c is greater than 0. And each time that we repeat this procedure, Note that the length of the interval AB is 1/2 of its previous length. Now we'll make some more observations about this in just a second. But we keep repeating this 3-case procedure. And one of two things is going to happen. One thing that could happen is one of our midpoints is exactly the solution we're looking for. We hit the jackpot and we print out the solution and we terminate the program. It probably won't happen, but it could. But we'll talk about the other possibility in just a second. We stop repeating our procedure when either of the following occurs. 1, f of c equals 0. Well, if this happens, we have the exact solution. And we print the solution is, and we print the value of c, and we terminate the program. We hit the jackpot. We got the exact solution. It won't happen often, but it could happen now and then. The other thing that, if this doesn't happen, and it probably won't, then what will happen is that the difference between B and A will eventually become less than our tolerance. We're cutting the interval AB in half each time and renaming the new endpoints A and B. So let's see, if we take an interval of length 1 and cut it in half 10 times, let's see, 2 to the 10th is 1024. So 1/2 to the 10th is 1 over 1024, or less than 0.001. Well, suppose we do it. Suppose we cut the interval in half not 10 times, but 20 times. Well, let's see. 10 to the 20th is 2 to the 20th is 2 to the 10th times 2 to the 10th. And so that's 1024 times 1024. That's more than 1 million. So 1/2 to the 20th is less than 1/1,000,000th. It's 0.0000001. 0.5 zeros and a 1. That's if we repeat this procedure 20 times. If we repeat it 30 times, then the interval from A to B is less than 1/1,000,000,000th. That's decimal point, 8 zeros and a 1. Now, do we really want to do this over and over and over again 30 times? No. But our computer doesn't mind. It'll do it in a tiny fraction of a second. So if this doesn't happen, and it probably won't, this will happen. And when it does, any point P in this interval will be a good approximation for our solution x0. Well, why is that? Well, here's our interval from A to B, a tiny interval, but we've blown it up. Here's our solution x0, and here's any point P in the interval that we just pick at random. Here's the difference of P and x0. It's this distance right here. This is the difference between P and x0, which is a heck of a lot less than the length of this interval, B minus A. And B minus A is less than our tolerance. So at this point, when this happens, any point P in our interval will be a good approximation. So which point in the interval should we pick to be P? Well, we'll vote on that. Class vote. Okay, everybody? The votes are in and the decision is unanimous, somewhat arbitrarily, but unanimously. We let the midpoint C of this last interval be our approximation for the solution.